Good afternoon, judges. Today we're going to present to you the photodecomposition of methanol and production of hydrogen catalyzed by dye-sensitized titanium dioxide nanoparticles. I'm Ethan.
I'm Arnold.
I am Tom.
And I'm Isaac.
First of all, what's methanol? Methanol is a substance commonly found in cigarette smoke and new furniture. However, it's harmful to humans because it irritates our eyes, nose, and throat, and it's also carcinogenic. So here I'll compare the traditional photocatalysis method and our own photocatalysis method. So here you can see, both the dye and titanium dioxide nanoparticles are photoexcited by visible light and UV light respectively. This generates an electron hole pair and allows oxidants, such as superoxide ions and hydroxyl radicals, to oxidize methanol. And in our improved photocatalysis method, the photoexcited electron of dye can be transferred to the conduction band of the titanium dioxide nanoparticles. This oxidizes the dye and it can act as an oxidizing agent of methanol as well. So our photocatalysis method increases the decomposition rate and allows the wavelengths from visible light spectrum to be absorbed, compared with the traditional one, where titanium dioxide nanoparticles have a large band gap and can only absorb UV light, and hence requires doping and sensitizing in order to widen the light spectrum to be absorbed. So here are some absorption spectrums. As you can see, the titanium dioxide nanoparticles have a narrow absorption spectrum. Therefore, we have to sensitize it with dyes in order to widen it, allowing more wavelengths of light to be available for excitation of electrons.
And now I'll show you the experimental setup. As you can see in the picture, there's a methanol fan, a methanol meter, and a set of sieves and some LED light. In the experiment, visible light emitted by induction coil-powered LED decomposes methanol on dye-sensitized titanium dioxide nanoparticles. The dyes are sprayed onto the sieves, like the picture on the left. 4 dyes are extracted, including chlorophyll from spinach, anthocyanin from black beans, curcumin from gingers, and beta-carotene from carrots. Now move on to the preparation of sieves. To standardize the preparation, the volume of solution is fixed as 100 cm3. We weigh the sieves before and after the preparation to calculate the change of mass, which is the amount of dyes sprayed onto the sieves. As you can see in this table, since the masses of dyes are different on each sieve, we group them to attain equal masses for each group to ensure fairness.
And now I will talk about the calibration of the methanol meters. We use 5 experimental setups concurrently and to maintain constant experimental conditions, for example, the temperature and the humidity. And because the meters have different sensitivities, so we need to calibrate them in order to reduce the bias of the readings. We prepared a filter paper with 0.05 milliliter of 0.037% methanol solution, and we stick it onto a mini portable fan. And then we record the data until the values of the meters were constant for around 10 minutes. And then we compare the values we taken from different meter and we divide it over the mean, and the ratio is applied to the experimental graphs.
Now I will talk about the results and conclusion. The effect of various wavelengths of light and different types of dye on photodecomposition of methanol by titanium dioxide nanoparticles was investigated. To standardize the results, we took the difference between the peak value and the value 20 minutes after the peak for calculating the methanol decomposition rate. Comparing different setups, beta-carotene dye coupled with green light showed the best performance, with a decomposition rate of 0.36 millimole per dm cube per minute. Although using UV light coupled with titanium dioxide nanoparticles showed a similar decomposition rate of 0.343, we suggest that the same performance can be achieved by using an energy-saving and less hazardous way. Taken together, our device is a more preferable one for methanol removal. For hydrogen generation, chlorophyll dye coupled with red light can generate 4.5 ppm of hydrogen per hour, which proves the possibility for producing hydrogen during the photocatalysis process. In the future, combination of other dyes and other wavelengths of light will also be investigated to find a combination we can achieve the highest efficiency. Thank you.